Good evening, everyone. So today in this session, we'll be discussing about the electromagnetic waves, right? We're done with the alternating currents, right? So this will be the last unit of the electromagnetism, right? Then in the next session, we'll be starting from the atoms and nuclei, right? So let's finish this unit, electromagnetic waves in this session, right? So electromagnetic waves are very important component of our daily life, right? You can see that we have a light, right? The light has a dual nature, right? It has both particle as well as the wave nature, right? And the light itself is a electromagnetic waves, right? Where different types of waves, right? Where mechanical waves, right? Where electromagnetic waves, right? In mechanical waves, we have two types of waves, right? Or in waves general, we have two types of waves. One is transverse wave, and another is what we call as longitudinal wave, right? So in mechanical waves, we have the sound wave, right? So mechanical waves are all those waves, right, which require the material medium, right, for their propagation, right? You know that in case of sound, if there is no medium for the propagation of the sound wave, then the sound cannot be propagated from one point to another point in a space, right? But in case of electromagnetic waves, they do not require any medium for their propagation. We can transmit electromagnetic waves without any medium, right? You know that in our outer space there is no medium, right? And light is an electromagnetic wave, and we receive the electromagnetic waves from sun. So electromagnetic waves actually reach earth without any medium, right? Without any medium. So such waves we call as electromagnetic waves, right? The specialty about the electromagnetic waves is that they do not require the material medium for their propagation, right? Now the question is that what led to the concept of the electromagnetic waves, right? So the history about the electromagnetic waves is that uh, whenever an electric field changes, right? Whenever an electric field changes, the varying electric field always produces a changing magnetic field, right? So the if electric field in some region changes, the change in the electric field produce changing magnetic field, right? And vice versa. If we change the magnetic field, then changing electric field is also developed, right? And this concept of changing electric field, which produces the varying magnetic field, or the varying magnetic field, which produces the changing electric field, actually gives rise to the transverse wave, which we call as electromagnetic wave. So, electromagnetic waves are transverse in nature. It means that uh, it propagates perpendicular to the electric field vector and the magnetic field vector, right? So they have the time varying magnetic field, time varying magnetic field, and time varying electric field, right? And both the time varying magnetic field and time varying electric field actually are perpendicular to each other or normal to each other. And also the direction of the propagation is perpendicular to the direction of the electric field vector and the magnetic field vector, right? You can see here in this diagram, you can see here in this diagram also, right? This is the propagation of the electromagnetic wave, right? This is the propagation of electromagnetic wave, right? This is the pictorial representation or the geometric representation of an electromagnetic wave. So you can see in this picture, the electromagnetic wave is propagating along plus x direction, right? It's propagating along plus x direction, right? And the electric field vector is actually perpendicular to the direction of propagation, and magnetic field vector is also perpendicular to the direction of propagation, right? So electric field vector is along y direction, right? It's along y direction, and magnetic field vector is along z direction, right? It's along z direction. So in an electromagnetic wave, the electric field vector and the magnetic field vector are always perpendicular to each other and perpendicular to the direction of propagation as well, right? So this was all about the electromagnetic wave. They do not require any material medium for for their propagation, and it has got a time varying magnetic field and the time varying electric field as well, and both are normal or perpendicular to each other as well as to the direction of propagation, right? Now, the history of electromagnetic wave is that Maxwell had predicted the electromagnetic waves, but he had predicted the EM waves theoretically, right? So theoretically, he actually predicted that whenever accelerated charge sets up, right? Whenever we have an accelerated charge, the accelerated charge sets up an magnetic field around it, right? And that magnetic field is actually a varying magnetic field, right? Because it's accelerating. Whenever accelerating charge accelerates, it produces a varying magnetic field, and that varying magnetic field gives rise to the varying electric field. In turn, we can say that accelerating charge gives production to the electromagnetic waves, right? Or it gives rise to the electromagnetic waves, right? So Hertz was another scientist in 1887. He produced actually experimentally and detected the electromagnetic waves, right? So Maxwell had predicted the electromagnetic waves theoretically, right? But it was Hertz who actually produced and detected the electromagnetic waves experimentally, right? And the wavelength was about 6 micrometer, right? It was 6 micrometer. And later on, an Indian scientist, that is J.C. Bose, it's Jagdish Chandra Bose. He was also successful in producing the electromagnetic waves in lab, right? And wavelength ranged from 25 mm to 25 mm. So this was the some basic historical background, right, about the electromagnetic waves, which was predicted by the Maxwell, and later on it was experimentally done by Hertz, produced by the Hertz, and experimentally detected by the Hertz, right? And later on, it was also produced by the electromagnetic waves were produced by the GC Bose also, right? So it has a theoretically it was predicted by Maxwell, right? It was a great prediction by the Maxwell, right? And later it was experimentally proved, right? Now let's discuss the bit about the concept of the displacement current, right? Displacement current, right? We know that when a capacitor is charged, right? Whenever a capacitor is charged, let's suppose we are connecting this capacitor with a battery, and this capacitor starts charging, right? And this end of this plate of this capacitor attains positive charge, and this end of the plate capacitor attains negative charge. And we know that the space between the plates of the capacitor is filled with the air, right? Filled with the air. Now the question is that even if the circuit is not completed, there is a gap between the two plates of a capacitor. How is it possible to have the conduction of the current in this gap also, right? So this was a question, right, which was not answered, right? Still, we are charging the capacitor, polar plate capacitor, right? There is a air present in the capacitor. How it is possible the current still flows through the capacitor? If the current I is entering this positive plate, how is it possible the current same I is coming out of this plate when there is a gap between the two plates, right? So we know that when a capacitor charges, right, the charge continuously increases on the plates of the capacitor, right? And because of this varying charge, we know that for any conductor, the electric field is equal to the electric field near the surface of a conductor is nothing, it's sigma upon epsilon naught, right? Sigma is the charge density, right? So as the capacitor keeps on charging, right? As the capacitor keeps on charging, right? Then the charge on the capacitor increases, and the charge of the capacitor increases, charge density increases, or we can say the electric field near the surface of this conductor changes, right? So it has got a time varying electric field actually, right? Time varying electric field. So we can write the sigma as Q upon A epsilon naught, right? Q upon A epsilon naught. So this is the electric field near the surface of this conductor, right? Now the question is that what is actually happening there, right? When there is a gap between the two plates of a capacitor, right? This was answered by the Maxwell, right? He introduced the concept of displacement current, right? Displacement of current concept was actually introduced by the Maxwell. What he did that he did actually a mathematical correction to the Ampere circuit law, where he introduced the concept of displacement current, right? So what was the concept here? He said that since the charge is changing, right? Charge is changing, so the electric field is varying near the surface of this conductor, right? So he said that this varying electric field is actually analogous to the current, right? It's actually the analogous to the current. So instead of the current flowing through this gap, actually what is happening there, the electric field is changing, right? So this is the analogous, or this we can say this is the replacement to this current, right? And because of that, we are getting the same current IC from the negative end of this negative plate of the capacitor, right? So and this current he called as displacement current. This current he called as displacement current. It was the replacement for this current I, normal current, right? He said that it's the change in electric field, right, which is analogous, or we can say it's equivalent to the current, right? It's equivalent to the current, even if there is a gap between the two plates of a capacitor. So This works like a current, right? This changing electric field here works like a current, and this current we call as displacement current, right? This is the concept of the displacement current, right? So this current was called as displacement current, or we can say the current id is flowing, the current id is flowing between this space, right, or between the two plates of a capacitor, right? So you can say that you can see that if E is the electric field, right, Q is the charge, then the current is continuously varying because the charge is varying. We can write dq over dt as current I, right, current I, and this current I will be equivalent to the displacement current T, right? Because the same amount of current must flow through this region, through this space, so that the current entering the positive plate must leave the current from the negative plate, right? So this will be equal to displacement current. So this current in this region is what we call as displacement current. That's IT, right? That's IT, and it is equal to I, right? Now, this electric field is varying because the charge is varying, right? Charge density is varying. So if we take the time derivative of this electric field, dE over dt, right, we will get 1 upon A epsilon naught, right? 1 upon A epsilon naught dq over dt, right? dq over dt, right? And this dq over dt is nothing. This is I, right? This is I. You can write it equal to I upon A epsilon naught, right? I upon A epsilon naught, correct? This is I upon A epsilon naught. So this I is equal to ID. This is the displacement current, right? ID upon A epsilon naught. Or the displacement current is nothing. Displacement current in this region is nothing. That's A epsilon naught, right? dE by dt, right? dE by dt. So this is what we call as displacement current, right? This is nothing. This is the displacement current, right? So this is nothing. This is displacement current, right? This is the displacement current. So displacement current is nothing. It's the A epsilon naught times dE upon dt. It means the derivative of the electric field vector, electric field with respect to the time. So the current here in this region is nothing. That's ID. And this current we call as displacement. That's A epsilon naught dE over dt, right? Where E is the electric field, right? This is the electric field. So this is the electric field, right? So we can rewrite it as let's suppose we know that ID is equal to A epsilon naught dE upon dt, right? That's the first derivative of electric field vector with respect to time. Or we can write it as like this epsilon naught E into A, right? E into A upon dt, right? And you know that E into A is nothing. E into A, electric field is perpendicular to the plates of this capacitor, right? So area of this capacitor is along the direction of the electric field. So it means that it's nothing. E into A is the flux, right? E into A is the flux through the area, right? We can write it as flux, electric flux, right? Phi E. So it means that displacement current is nothing. It's epsilon naught times rate of change of this, what we call as uh, electric flux with respect to time, right? So it's nothing. Displacement current is epsilon naught d phi e upon dt, right? Or rate of change of electric flux with respect to time, right? So now apart from the current I, there comes the concept of displacement current as well, right? So we also studied about the Ampere's circuit law. So Ampere's circuit law says that integral of P dot dl closed line integral of magnetic field is equal to mu naught times current enclosed, right? Current enclosed. Now we can have another current. We can also have the displacement current, right? We can also have the displacement current. So there are two currents. One we call as free current, right? Another we call as displacement current. So the total current enclosed can be equal to mu naught times I plus ID, right? This is the electronic current and this is the displacement current, right? So this completes, or we can say this is the corrected Ampere circuit law, right? Corrected Ampere circuit law. Corrected Ampere circuit law. This is the corrected Ampere circuit law. And this is also what we call as Maxwell's equation, right? This is the Maxwell's third equation. Maxwell's equation. It's one of the Maxwell's equation, right? one of the Maxwell's important equations, right? So integral of B dot dl will be equal to mu naught I enclosed, where I enclosed can be electronic current plus the displacement current, right? Where the displacement current is zero, we can just put there displacement current equal to zero uh, to calculate the magnetic field, right? Now we can write different Maxwell's equations, right? First Maxwell's equation is nothing, it's the Gauss law, right? It's the Gauss law. Gauss law for the electrostatics, right? Gauss law for the electrostatics. And the Gauss law for the electrostatics is nothing, it's integral of E dot ds, right? That's equal to charge enclosed, right? Q enclosed upon the epsilon naught, right? Upon the epsilon naught. And so, next equation is what we call as next equation is Faraday. We can write Ampere's second law, right? Ampere's law, right? This is the next second Maxwell's equation. That's nothing. Integral of P dot dl, right? That will be equal to mu naught I enclosed, right? I enclosed. Or we can write it as mu naught electronic current plus the displacement current, right? Or we can write it as equal to mu naught times electronic current plus the displacement current is nothing. Epsilon naught d phi e upon dt, right? D phi e upon dt. Here phi is the electric flux, right? Third equation is Gauss law for the electromagnetism. That's the flux, total flux of the magnetic field over a closed surface, right? That's equal to zero, right? And this says that this means that magnetic monopoles actually do not exist, right? Magnetic monopoles do not actually exist, right? Monopoles do not exist, do not exist. And the fourth equation is the Faraday's law, right? We know EMF developed in a circuit, right? Where we have changing magnetic flux, right? Or we can say this is the induced EMF, or we can write it as integral of electric field with respect to the line. The integral of E dot dl, it's nothing, it's equal to minus d phi b upon dt, right? D phi b upon dt. So from here you can see that the changing magnetic field can give rise to the changing electric field as well, right? So this is the importance of these Maxwell's equations, right? So it Maxwell's equations actually summarizes the whole electromagnetism that we have studied till now. So it actually summarizes the whole electromagnetism that we studied till now in the form of these four equations, right? In the form of these four important equations, right? Now, talking about the electromagnetic waves, there are certain properties, right? There are certain properties that electromagnetic waves actually satisfy, right? First of all, the equation of the electromagnetic waves, right? The equation of the electromagnetic waves is d square e upon del square e upon del x square, right? That's equal to mu naught epsilon naught, right? Del e upon del t, right? Del e upon del t, right? So this is the what we call as wave equation for the wave equation for what we call as wave equation for the electromagnetic waves, right? It should be del square E upon del T square, right? So this will be the wave equation for the electromagnetic wave. Similarly, we can write it equal to in the form of the magnetic field del square P upon del x square. That will be equal to mu naught epsilon naught del square B upon del T square, right? Right. So this is the what we call as this is what we call as this is the second derivative with respect to x. This is nothing. This is what we call as the wave equation, right? This is wave equation. Wave equation, right? So this is the wave equation, right? This is the wave equation of the electromagnetic wave, right? So if we try to solve this wave equation, we can have different solutions, right? Different solutions for this wave equation, right? The electromagnetic waves travel through the vacuum, right? The electromagnetic waves travel through the vacuum with some speed. That speed, what we call as speed of light, right? That's equal to 1 upon under root of mu naught epsilon naught, right? where mu naught is permeability and epsilon naught is the permittivity of the medium, right? And the third point is the electric and magnetic fields of an electron are perpendicular to each other and also perpendicular to the direction of wave propagations. So that's the reason we say that these are actually transverse wave, right? These are actually transverse wave, right? So the direction of the electromagnetic wave, right, is given by the cross product of the electric field vector and the magnetic field vector, right? Let's suppose eta cap is the direction of the electromagnetic wave. It will be given by cross product of direction of cross product of E cross B. So E cross B will give us actually the direction of the electromagnetic wave, and E and B will always be perpendicular to the direction of propagation, right? Direction of propagation, right? So the instantaneous, if we solve this wave equation here, this wave equation above, right, we will get the solution of this electromagnetic wave, right? The solution of this electromagnetic wave can be in the form of, that will be E is equal to, right? E will be equal to Em sine of omega t minus kx, right? Or B will be equal to Pm sine of omega t minus kx, right? So these are the solutions of electromagnetic wave, right? These are the solutions of the electromagnetic wave. So all both the solutions actually satisfy this equation, this wave equation, right? So the where Em is nothing, Em what we call as amplitude, right? This is the amplitude of the electric field, right? Amplitude of electric field, and Bm is nothing, it's the amplitude of the magnetic field, right? Omega here is nothing. Omega is the angular frequency, right? It's the angular frequency. Omega here is angular frequency, and k is the propagation vector. K is the propagation vector. Propagation vector. So omega is the angular frequency, propagation k is the propagation vector, and this k propagation vector actually tells us about the direction of flow of the electromagnetic wave. So here, since k is actually in product with the x, it means that the wave is propagating actually along x direction, right? It's actually propagating along plus x direction, right? It's actually propagating along plus x direction, right? So k gives the direction of the electromagnetic wave. Omega is the frequency, right? Omega is the frequency, and the electromagnetic waves, right? Electromagnetic waves carry energy. The rate of flow of energy crossing a unit area is described by a quantity. That's what we call as the Pointing vector, right? So Pointing vector gives actually the flow of energy, flow of electromagnetic energy, that's given by 1 upon mu naught electric field vector crossed with the magnetic field vector. So this is nothing. This is what we call as Pointing vector, right? This is Pointing vector, right? Pointing vector. So Pointing vector actually tells us about the flow of energy, direction of flow of energy, right? Direction of flow of energy. And there is one important relation between the electric field and the magnetic field at any instant, right? So E by B, ratio of E by B will always be equal to C in vacuum, right? Where C is the speed of light. So the ratio of electric field and the magnetic field always gives the speed of light in vacuum, right? And this Pointing vector actually represents the direction of propagation of the electromagnetic wave, right? Direction of propagation of the electromagnetic wave, right? One more important point is that we know that whenever let's suppose that this is the surface here, right? Surface here. This is the surface here, and on this surface, the electromagnetic waves actually strikes. Light is striking, right? Light is striking continuously. So when these electromagnetic waves strike the surface, they transfer the momentum to this surface, right? They transfer the momentum to this surface, right? So they transfer the momentum and also exert the pressure, right? And that momentum, that pressure or the momentum we call as radiation pressure, right? Radiation pressure. And if these electromagnetic waves are completely absorbed, right? If these electromagnetic waves are completely absorbed, then the radiation pressure, right? And the radiation pressure will be nothing, right? Or we can say the momentum, the radiation pressure on this will be equal to, it will be S upon C, right? Where S is the Pointing vector, C is the speed of light, right? And if there occurs a perfect reflection, right? This is for perfect absorption. If the perfect reflection occurs, right, it means that electromagnetic wave is propagating and it gets reflected back. 100% reflection is there, right? Wave propagates and strikes the surface, right? And there is the 100% reflection or propagation of this electromagnetic wave. Then in that case, the radiation pressure will be equal to 2 times S upon C, where S is the magnitude of the Poynting vector and C the speed of light. So this is the radiation pressure, right? Radiation pressure. The electric fields and the magnetic fields of a sinusoidal plane electromagnetic wave propagating the x direction can also be written as, right. So if electromagnetic wave is propagating in the x direction, we can write its equation as E is equal to, right, Em, right, sine of omega t minus kx, or kx minus omega t, right. And magnetic field will be Bm sine of omega t minus kx, right? So these are the solutions of the electromagnetic wave, or we can say this is the equation of the electromagnetic wave, or we can say these are the electric field equations for electromagnetic wave and magnetic field equation for the electromagnetic wave, right? Now, talking about the intensity. Intensity is the energy falling per unit area per second, right? Let's suppose this is the area, right? This is the area A, right? This is a plate of area A, right? And there is some electromagnetic radiation falling on this area, right? Right, on this area. Now we have to define the intensity of this electromagnetic wave, right? So the intensity I of this electromagnetic wave is nothing. It's the energy, right? Total energy falling per unit area per unit time, right? Per unit area per unit time. So this is nothing. This is the intensity, right? This is what we call as intensity of electromagnetic wave, right? Intensity of electromagnetic wave. Intensity of electromagnetic wave, right? And the intensity of electromagnetic wave is also given by the average of this Poynting vector, right? Average of this Poynting vector, or we can say it's the average of this E cross B, right? E cross B. So intensity, or we can say uh, average value of Poynting vector taken over one cycle gives actually the what we call as the intensity of a radiation, right? So this is how we can calculate the average intensity, right? And one more important point is that average of the Poynting vector that gives us the intensity. That's nothing. That's equal to half of, right, 2s mu naught, right. That's equal to the amplitude of this electric field vector, right, multiplied with the amplitude of this magnetic field vector, right. That's equal to Em into Bm upon twice mu naught, right. We also know that E upon Em upon Bm is nothing. That's equal to C, right. That's equal to C, or we can write Em here equal to Bm into C, right. Where Em is nothing. This is the maximum value of the electric field. Bm is the maximum value of the magnetic field, right. So from here we can substitute the value of Bm here, Em upon C, right. So it will be equal to E square, right? E square upon 2C into mu naught, right? You can write it like this also, right? This is nothing. This is the average intensity, or we can say this is the intensity of the electromagnetic wave, or we can say this is the average value of the Poynting vector, right? Average value of the Poynting vector. Now, talking about the different electromagnetic spectrums, right? We have different types of electromagnetic waves, right? There are different types of electromagnetic waves we have. Depending upon their frequencies, right? Depending upon their frequencies, the different types of electromagnetic waves that we have, right? Uh, in the order of the range or the spectrum of the electromagnetic waves, it's actually the band of the electromagnetic waves with different set of frequencies, right? Or different set of wavelengths, right? Different set of frequencies or different set of wavelengths. So we can see here, we can see here the electromagnetic wave with the highest frequency is what we call as gamma ray, right? It's the gamma ray. So gamma ray, right? Gamma rays are the electromagnetic waves of highest frequency, right? Gamma rays are the electromagnetic waves of highest frequency. Then we have what we call as X-rays, right? We have X-rays, right? We have X-rays, right? So we also have the what we call as ultraviolet rays. That's UV rays, right? UV rays, right? And then after UV rays, we have what we call as visible region, right? Visible region, visible region. So visible region, in visible region, we have seven types of frequencies or the wavelengths. That's the VPure, right? VPure. That's violet, right? Violet, indigo, blue, yellow, orange, and red, right? Right. So we have a band of spectrum, a band of wavelengths, right? Depending upon their frequency, we have gamma rays, we have X rays, UV rays, visible region, right? Then we also have what we call as infrared rays, right? Infrared waves. And after infrared waves, we have uh, microwaves also, right? Microwaves. And then we have finally radio waves, right? Radio waves are actually used for the propagation or for the communication purpose, right? So gamma rays are the rays of highest frequency, right? They are the waves of the highest frequency, highest frequency or least wavelength, right? Highest frequency or least wavelength, highest frequency or least wavelength. And similarly, we have here radio waves of least frequency, least frequency or higher wavelength, least frequency or higher wavelength, right? So all these waves have different application. You know that whatever from all these electromagnetic spectrum, uh, the waves or the frequencies which are very useful for us, that's the visible region, right? Because of this region, we are able to see different objects around us. So visible region is very important for us for the vision, right? Gamma rays are the very penetrating, right? They have the highest penetrating power, right? Gamma rays. So gamma rays, we should always protect ourselves from all these rays, right? Gamma rays, X rays, UV rays, right? Because they have the highest penetrating power and it can damage our eyes or skin as well, right? So visible region are very important for us because our eyes are very sensitive to this region, and because of this region, we are able to see everything around us, right? So they become very important for our vision. That's the visible region, right? So this was all about the electromagnetic spectrum, right? Now let's try to solve a question on this, and we'll wrap up this chapter. That's the electromagnetic waves. So it was a very short chapter, right? And then we'll be discussing we'll be starting with the atoms and nuclei in the next lecture, right? So let's have this question, right? In a plane electromagnetic wave, the electric field oscillates sinusoidally, right? In a plane electromagnetic wave, the electric field oscillates sinusoidally at a frequency of 10 into 10 to the power 10 hertz, right? The frequency here is given as uh, 2 times 10 into 10 to the power 10 hertz, right? 2 times 10 to the power 10 hertz, right? And the amplitude of electric field, that's given as 48 volts, right? That's 48 volts per meter, right? We have to calculate the amplitude of the oscillating magnetic field, right? Amplitude of the oscillating magnetic field. We know that the relation between the electric field and the magnetic field is that E upon V is equal to CV. That's the speed of light. Speed of light, right? We know the value of E, right? Or we can write E upon C is nothing. That's E upon C is equal to uh, B, right? E upon C is equal to B. So the value of B will be equal to E has got the value of 48 and C has the value of 3 into 10 to the power 8, right? That's equal to 16 into 10 to the power minus 8, right? Tesla, right? This much will be the magnitude or amplitude of the magnetic field, right? This will be the magnitude of the magnetic field, right? There is an important concept what we call as if we write the equation of wave for electromagnetic wave, that's Em omega t minus kx, right? Kx, right? This k is what we call as a propagation vector, right? This is nothing. This is the propagation vector. This k is nothing. This is what we call as propagation vector, right? Propagation vector. And this k has the value that's equal to 2 pi upon lambda, right? 2 pi upon lambda. Where lambda is nothing. Lambda is the wavelength, right? Lambda is nothing. It's the wavelength of electromagnetic wave, right? And similarly, we can write omega. This is the angular frequency. That's 2 pi into f. Or we can write the frequency of electromagnetic wave as angular frequency upon 2 pi, right? So this is the frequency of electromagnetic wave or the wavelength of the electromagnetic wave, right? So that's it with respect to the electromagnetic waves. We have finished this topic of electromagnetic waves. It was a very short topic. In the next topic, we'll be starting with the atoms and nuclei. That will be discussed on Monday. So till then, take care and goodbye.